Hello students, this is part 2 of chapter 4 and this section is covering cyclohexanes. We're going to really understand the conformations, understand energy differences, and you guys will need your models, so grab them if you don't have them yet. So the first thing we want to do is look at different chair flips. I want you guys to build a 6-membered ring. It might be nice to put the axial substituents, highlight them with a different color ball, and we're going to look at different chair flips. So if we look at this left structure here, I just happened to draw the chair this way. What I'm going to do for the chair flip is take carbon 1 and push it down, and take carbon 4 and push it up. The center 4 will be essentially the same, but you can see 1 is down here and 4 is up here. What that does is turn all the axials equatorial. So that's the first step. When you do a chair flip, anything axial becomes equatorial and anything equatorial becomes axial. The other thing is that I'm going to teach you something that I think is a very useful tip, and it's that the substituents maintain their up or down positions. So for example, on carbon 1, the black ball is up, and this other substituent is down. Just literally, if you look at the picture, it's pointed up, and this one's pointed down. Not straight down, because it's not axial, it's equatorial. After the chair flip, we're still at C1, the black ball is still up, even though it's equatorial, and then the other substituent is down. So that's very, very useful when you start naming things cis or trans and tracking where substituents should be when you redraw a structure after a chair flip. So I'm going to show you in the video here. I have my 6-membered ring, and I have it in a chair. The chair should be 4 flat in the center, and then 1 down, 1 up. So it's like someone sitting on a chair. I also made my white balls all axial, and everything equatorial I left without a ball, just a bond. So we're going to do a chair flip. I'm going to take, let's call this the C1. I'm going to push it down. Notice I don't do anything else. I just push that down, twist it down, and twist the other guy up. Now I have my chair flip. It's still a chair. And notice what happened. All of those white balls went equatorial. And all of the other equatorials are now straight up and down. You should be able to set this on a table if you did that correctly. And the axials are straight up and down. The other thing is after a chair flip, let's focus on this C1. The ball was up, it's still up, and this guy's down. So when you redraw chairs, it helps to track if a substituent is up or down, and draw it in the flip up or down, because that's always maintained. Because you don't know if equatorial is not going to stay equatorial. Okay. The next thing we need to talk about is different energies. Obviously, these can go back and forth. This is an equilibrium when you have a chair structure. If there's nothing on it, it's just going to go back and forth equally. But if there's a substituent on it, it has an option to be equatorial, such as this bromine, or bromine, or axial. So put a bromine on your ring. And what I recommend is take your model with all the balls axial, or whatever's highlighted axial, and take one of those axial guys and replace it with something else to represent a bromine. So I just replaced it. I now have an orange bromine. And so my bromine can be equatorial, or I could do a chair flip and make it axial. The problem with axial is it bumps into, or there's repulsion with the 2 axial H's. So we call this a 1,3 diaxial interaction, because it's 1, 2, 3 carbons away, and you have this axial two axials, so diaxial interaction, and there are two of them. So this is going to be less favorable because of this repulsion. So this is going to cost you something. There's going to be what we call steric strain. So it's higher in energy. So the preferred conformer will be the one with the bromine in the equatorial orientation. So here I have my chair, the bromine further out away from the ring, that's preferred. The chair flip gives this bromine axial, and it's going to have repulsion with these guys. This is a 1,3 diaxial interaction, and this is a second 1,3 diaxial interaction. So this is going to cost you some money. We can talk about those numbers in a bit. But what's useful is if you know that energy, the difference in energy, you can actually calculate the population of each conformer. Or if you know how many are in a certain conformer, you can calculate the cost of that strain. So let's look at an example of methyl. Methyl equatorial here is pointing away, out, not bumping into other guys. Versus this axial, you have this repulsion, this A13 strain here, this methyl bumping into this H and this methyl bumping into this H. So you have steric strain, the axial is less favored, so much so that if I took a snapshot, only 5 molecules would be axial in the axial conformer, and 95 would be where the methyl is equatorial. So you can actually use this to calculate the cost of the methyl axial. You can use something you learned in Chem 150 or your second semester general chemistry course, using delta G equals minus RT natural log of K, where the K is the equilibrium constant of product over reactant. You can calculate a Gibbs free energy of 7.28 kilojoules per mole, which is 1.74 kcals per mole. So that means that's the cost of these two A13 strains. And so each one of these is about 0.9, which was the same we said was a gauche. And just to let you know, this is actually a gauche interaction that we talked about when we were talking about Newman projections. So if I look down this bond here, and I have my methyl up, and I have this ring off to the left, you can see the methyl up, and this here is like a methyl group in a gauche, right? Methyl gauche is like this, and it's really this hydrogen bumping into this methyl. In a gauche, you have methyl, that's also in gauche butane, the same sort of interaction. So two of these, we said a gauche was 0.9, two of these is about 1.8. Okay, different substituents have different values for the A13 strain. We also call that A value for short. And so let's see, larger substituents are going to be worse and have greater A13 strain. If you have a tert-butyl group, it's 5.4 kcals per mole. If you have something smaller like a nitrile, that's going to be 0.2. So you have here an OH group in this cyclohexanol, this alcohol. The equatorial is going to be favored. You can see that by the double-headed arrow. And the axial is less favored by 4.2 kilojoules per mole. Here, notice that the units are a little different. They're different. Here it's kcals, here it's kilojoules. A tert-butyl is much more offensive. So here equatorial is much more favored because now you have 3 carbons in the axial position. You're going to have much more repulsion. So the axial is quite a bit less favored. Disubstituted also has a gauche interaction that's a little bit different across the ring. So if you put 2 groups in a 1-2 position here, If you have a methyl axial, you're going to have those two diaxial interactions we just talked about. Methyl here interacting with the two hydrogens. However, if you add another methyl equatorial, it's not that it doesn't have any effect, because it does have an effect. If you look down this bond, you can see that you have a Gauche interaction on top of this axial interaction with these two hydrogens. So let's just practice a couple things. Just similar to what we just saw, you have a 1,2 dimethyl, but in a cis conformation and a completely separate structure in a trans, one up and one down. Notice these are separate, not in equilibrium. So what I want you to do is, first of all, build a model of each of these, and then draw the structures as a chair and draw their chair flip. When drawing a chair flip, it's easier to keep track of up and down substituents to draw in where they go. So pause this, take your time. This could take a little bit of time, and just go through this exercise, and then I'll go over this. So for the cis structure, both methyls are up, or they could be both be down. And so one chair, let's just name it, number it 1, 2 here. You could draw the chair like this. You may have started with a different chair flip. Maybe you drew the right one first. That's fine. You could have put your methyls anywhere around the ring. You could have started here. Here I'm just showing it one up at the 1 position and another up at the 2 position. If you did a chair flip, 6 gets pulled down and 3 gets pulled up. What does that do? That makes this C1. So you see how numbering is really important to track. C1, even though you do a chair flip, keep the methyl up. Now it's axial and the H is equatorial, and keep the methyl at C2 up. C2 now up is methyl. So track the substituents when you draw flips with up or down. That's the easiest. These are the same energies, because in each one you have an axial methyl in each and an equatorial methyl in each. The trans is different. One is up, one is down. So you could have drawn this, one up, one down, both are equatorial. That's very favorable. If you do the chair flip, one up, one down, both are axial. Much less favored, the lower energy conformer out of all of them is the one where both are equatorial. Let's name cis or trans. So here I give a dibromo example. If both bromines are down, notice this has nothing to do with equatorial or axial. You have to look if they're both on the same side, both down or up, or one's up, one down. Both down in this case, or both up, we'll refer to cis. In this case, I show it as 2 dashes in the 1 and 4 position, 1 and 4. And then in this structure, in the 1 and 4 position, I have one up and one down. So one up and one down. Notice, just to let you know, I didn't put the bromines here. So if this was for this exact structure, you would have had Br here, and Br here, and Br and Br. And this would be trans, one up, one down. So there are a couple ways to depict this. You can draw the chair, you can write trans, and you can draw it with the dash and wedge. Study these depending on where the substituents are around the ring. There are different preferred ring systems. Again, equatorial is preferred. So here, this methyl conformer, where it's di-equatorial, is preferred over diaxial. We already went through this one. Dimethyl is preferred. Dimethyl, where they're both equatorial, is preferred. Sometimes you have a situation where one has to be axial. So put the one with the largest A value equatorial. So here, ethyl's bigger than methyl, will have the larger A value, put the ethyl equatorial. So this conformer is preferred. In this case, I have isopropyl, which is larger than ethyl. Isopropyl, equatorial is preferred. Our last slide in this video is talking about bicyclic rings, 2 rings here shown fused together. You can have different geometries here. So here I have the ring going down and up. So down equatorial, up equatorial, that's preferred. This is called transdecaling. The cisdecaling here forces one of those ring carbons down axial. And so you have a less favored ring system here. The transdecaling is more stable than the cis by 1.8 kcals. And just note, these are completely separate compounds. You cannot interconvert through a simple equilibrium to go between the two. You would have to break the bond and reform a new bond. Okay, that ends this section, and we will continue more with rings another time.